for the field pattern to be drawn. And we have said that a field line at a point gives the direction in which a positive charge would actually accelerate. 2, the other important point we need to note here is that the number of field lines per unit area is always proportional to the strength of the intensity. The number of field lines per unit area is always proportional to the strength of the intensity. This implies that if lines are closer together, then we have a strong field, and if lines are separated, then the field is a weak field. We already have derived the expression for electric field intensity, but for purposes of emphasis, because we used R, people did not know where was the R coming from. So for the electric field intensity at a point, we can say E due to a point charge. If we are interested in the expression of intensity due to a point charge, we can consider a charge Q at a point O, a distance R, from another point A, where we are going to put our test charge. The charge here is going to be considered as a test charge. If we are interested to find the electric field intensity here, then we have already defined electric field intensity as the force per unit charge here. If we want to find the expression for electric field intensity at point A, then we can take this as the general expression, but we want to find the expression of force at point A. At A, the force, which we are calling F, will be given by the product of the charges. This times the small charge out of R squared, if I have used the K here. Now, if this is the force expression, we have said that if we divide it by this charge here, then we get our expression for intensity as K Q Q out of R squared times 1 out of Q. And we were able to get our intensity expression, which I wrote here at the start. The distance R is the distance of separation between the known charge and the test charge at point A. And that means that our expression for intensity as area obtained will be K times the charge now out of R squared. And if we look at it, it implies that the intensity varies inversely proportional to the square of the distance between, which we normally refer to as the inverse square law. And mathematically, if we are to sketch a graph of intensity against distance R, it should be able to give us a graph of that nature. It should be able to give us a graph of that nature. Now, our dear students, so far, I want to emphasize that we know the expression for force, and we have tried to use it before. We know the expression for electric field intensity, and we should actually be informed also that electric field intensity is a vector quantity. It is a vector quantity, and therefore it implies that magnitude and direction need to be specified there when we are dealing with the calculation part. Now, we can talk about flux. if we consider a point charge, we said this is a test charge, which you can consider as a point charge. The number of field lines piercing through a unit area will be defined as flux. Flux can be defined as the number of field lines piercing through a unit area. The number of field lines piercing through a unit area. Once we know how to define flux, usually we use this symbol for flux, and flux is related to intensity. Flux is related to intensity by that expression. We are saying it's the number of field lines, and field lines, we notice that they carry intensity. Therefore, it means that we can also say that intensity is the same as flux over area. We can also say that intensity is the same as flux over area. And if intensity is the same as flux over area, we can hence be able to prove that since we are looking at spherical charges, the area, which we are calling A, can also be equal to the surface area. And therefore, if we are interested in intensity using flux, we can still look at this formula and be able to get intensity by looking at flux. That flux from here being equal to intensity times area, we can get the expression for relating flux and intensity, and area as this. But we are saying intensity is already known. So if we know intensity, then we can say that flux actually is the same as intensity, which I can say is kq out of r squared times the area. If the area is considered to be the surface area, we can get that as an expression. And if there is any need to use a formula to that effect, we can go ahead and substitute in for K to get flux being equal to actually charge out of, I'm substituting in for K, 1 over 4 pi epsilon r squared times our surface area here. When we simplify this, it should be able to give us the 4 pi r squared will cancel out, and we should be able to get an expression that relates flux, permittivity of free space, and charge. And this gives us charge out of epsilon as another expression that we need to know. So flux can also be equivalent to charge over epsilon, and in this case, this is always looked at as Gauss's law. For any sphere that is charged, for a charged sphere, the intensity is always equivalent to this expression. That is if the sphere is charged outside, and if the sphere is charged inside, we notice that the charge inside will be 0, and therefore the intensity inside will always be 0. This sketch would also be very important to show the behavior of intensity inside and outside the sphere. If we have a sketch here of intensity against distance, we can have distance, and we'll have our intensity here. If this sphere has a known radius, then we can always have our sketch, our intensity against distance, to verify. We already saw that intensity varies inversely proportional to the square of the distance. So you will discover that we will have this kind of graph if we are to indicate that intensity inside the sphere is 0 and outside the sphere the intensity varies inversely proportional to the square. Now, I would like us to focus on the use of this expression to do some numerical methods, numerical calculations, and later see how best we can use that formula to proceed to look at other parts of electrostatics. Last time, before I move ahead, I could make a small flashback to emphasize the issue of force. If I have a charge here, I will say this charge is 1 times 10 to the negative 9 coulombs. And I have another charge here, another positive charge of 9 times 10 to the power negative 9 coulombs again. There are 2 positive charges. I can be asked to find the force of attraction. The force of attraction between these spheres that are charged like this. If the distance between these spheres is known, I am simply interpreting this because we looked at it. I am simply interpreting it. We looked at these examples last time, so I want to simply interpret it and then we proceed. Assuming you are given charges 1 times 10 to the negative 9 coulombs, 9 times 10 to the negative 9 coulombs, and they are 30 centimeters apart, and they are asking you to find the force of attraction or repulsion between them. They will always give you this constant as 8.85 times 10 to the negative 12, or they can give you that 1 out of 4 pi epsilon naught is 9 times 10 to the power 9. Now, if they ask us to find the force of attraction, and hence ask us to tell, is that force repulsive or attractive? Basing on the charges and the field lines we just looked at, if the charges are similar, we say like charges repel. So the force is going to be repulsive, and the expression for force is simply going to be got by multiplying that Q1 times Q2 out of 4 pi epsilon over r squared is going to give you the force. So if they want the force, we shall get our 9 times 10 to the power 9, which ideally is the 1 out of 4 pi epsilon separated times the charge product over r squared. So we get this out and we multiply it by the charges, which is 1 times 9 times 10 to the negative 9 times 10 to the negative 9 divided by the distance. That is in meters, but it must be converted to SI and squared. So if force is required for numbers of that nature, you should be able to note that we shall use Coulomb's equation and be able to calculate the force. And I'm saying this type of force will actually be repulsive because the charges in this particular question are the same. I want us to move to calculations involving electric field intensity. Calculations involving electric field intensity. We have said, first of all, that electric field intensity is a vector quantity. We are able to now do numbers that involve force, and we have derived several other expressions. We have derived the expression for force for electric field intensity. We are yet to derive the one for electric potential, which hopefully we shall look at. So we can work through one number here, and the question says, I request that you capture this question that I'm going to write here, and then we work through it. Okay. let us use question 3. On the screen, we are going to use question 3. We are going to use question 3 on our screen. Question 3 on our screen, I want to draw it the way it appears as you copy the question. Question 3 on the screen. Question 3. We have 2-point charges of 3.8 microcoulombs placed at a point P and Q. At P, we have 3.8 positive. Micro is the same as times 10 to the negative 6. And at Q, we have 5.2 micro. Let us use this example. This is point R. This is point R. And what is important here is your ability to interpret, to understand the way we interpret this number here. Once you understand the interpretation of one number, you are good to go. Now, they are asking us to calculate the electric field intensity at point R. The assumption here is, the assumption we take here is that the electric field intensity at the point required, we will assume that that point has a unit positive charge. It has a unit positive charge there. And if it has a unit positive charge, it implies that the intensity, being a vector quantity, since this charge is positive, and we are saying the charge here is positive, it means that the intensity at point R, due to the charge at point, this was point P, due to the charge at point P is going to be, there is going to be a repulsive force. So it is going to be moving that side. I'll call it intensity due to P. And this is also positive, and that point is still positive. So the intensity there will still be a repulsive force. So the vector diagram will also show us that the intensity at R, due to the charge here, is also going to be going the other side. It is repelling this one. We have said like charges repel. Once we master that interpretation, that when they say find the intensity at a point, we assume there is a unit positive charge there. And we look at that charge and the charge here, and we judge whether there is an attractive field line or a repulsive field line. After that, we shall say, using intensity as K times charge out of R squared, where we have agreed that our K, which is 1 out of 4 pi epsilon, is going to be 9, substituted in as 9 times 10 to the power 9. We shall be substituting in that as our K, 1 over K. And that implies that if I look for EQ, the distances are key. They gave us the distances. This was 5 centimeters, and this was 12 centimeters. And if this is required, we would use Pythagoras theorem, since this is 90 degrees, to obtain this as 144 plus, it will give us 13 centimeters. So they want us to find the intensity at R. So if we are using charge Q here, this intensity at R due to Q is going to be given by K, which is that, times the charge, which is 5.2 times 10 to the negative 6, all divided by this distance here, squared. This distance squared. That is 5 times 10 to the negative 2 squared. So our EQ is going to give us a value that I will put later. I want to expect you to be calculating it. I'm going to put that value there. We can also look at intensity due to charge at P, which we shall call, this is intensity due to charge at Q. Due to Q. Intensity due to P, we shall call it EP. And this is again going to give us 9 times 10 to the power 9 times the charge there, which is 3.8, times 10 to the negative 6 out of the distance is 12 in SI units squared. Our EP will be, if we compute those values, we should be able to get EQ as 1.872 times 10 to the power 7. The power 7. These are volts per meter or newtons per coulomb. And then EP should be 2.375 times 10 to the power 6. I hope when you compute those are the values you get. But remember, they want the intensity here. I want to emphasize that. They want the intensity here, and we have been able to get those values so far. Now, this area is very crucial. Because this angle is 90, it implies that when I extrapolate this to get this field line that we have got, whose value we have got, and get that one, this is also 90. Now, the resultant, which is the intensity at R that we want, will act along the hypotenuse of those two. If we complete a parallelogram of field lines, we shall get our resultant, which I'm going to call ER, as that. And this will still be a 90. So it means that this is going to be shifted here, and therefore this followed by this will be equal to that. Using Pythagoras theorem, our resultant ER squared is equal to EP squared plus EQ squared. You are aware that intensity is a vector quantity, and therefore we shall get our resultant as the sum of the squares. 1.872 times 10 to the power 7 squared plus 2.375 times 10 to the power 6 squared. We compute and get the value of our resultant, which will give us, when you compute that, you should be able to get the resultant as approximately 1.887. 1.887 times 10 to the power 7. However, intensity, like I told you, is a vector quantity, so we need to find this angle. Which will be the direction. So the direction, which we are calling alpha, will be obtained by taking the tan. The tan of alpha, which will be the tan of our EP over EQ. And that will give us our alpha as the arctan when you compute. The arctan of course, if we get our EP, it is to the 6, and our EQ is to the 7. So we shall have 2.375 out of 18.72. EP divided by the other one will give us, if I take this as that, we get this force here, which is EP over that force, opposite of adjacent. And we will get that angle as, if you compute, that angle should be approximately rounded off to 7, I think. If you compute this, should be able to give you around 7 degrees. So intensity, in brief, is supposed to be a vector quantity, and therefore we can get it using that calculation. We can get it using that calculation. That is number 3. They wanted the field intensity at R. They wanted the field intensity at R. As you capture that solution, I could put another solution here. I am not going to rush you to potential. We can keep potential for another day. Let us focus on one, and we master it fully. Let us try to look at this other question that I'm putting here. Again, we have that diagram. This is 20 centimeters. This is 15 centimeters. Q1 is 3 microcoulombs, positive. Q2 is minus 2 microcoulombs. And then, yes, the question says that in the system, if you finish that, you can copy this question. I want us to work with this question up to the end of our discussion today. In the system of charges shown, find number 1, the electric field intensity at P. 2, the location of a point between P and Q, between Q1 and Q2, where the electric potential is 0. Three, the electric potential. At P. Dear learners, we have that question there. I had said we would look at electric potential next time, but this question forces me to briefly talk about it, but we shall emphasize more next time. Let us talk about electric potential. Because if I don't talk about it today, the questions that I'm going to leave for you may not be exhaustively utilized. Electric potential is denoted by symbol V, and we define it as the work done to move a unit positive charge from infinity to a point. And Ideally, this means if we are looking at potential, we look at a small change in work should be equal to force times the change in distance. Now, if we want to get potential, we normally integrate from infinity to a known point. And the expression we integrate here, I am simply going to bring it in, but I will expose this in our next meeting, that eventually we get potential as the integral of force. Force is normally charge, as we have seen, the product of charge, 1, 2, out of the times the constant, let me look at it like that, over, say, x squared with respect to x. But we have a negative there in our expression. Now, when you integrate this and we bring out this constant, these charges, the force expression, we'll get our work done. Eventually, our work becomes equivalent to the force expression, which is the constant times the charge integral of, say, 1 out of x squared dx. And this will give us an expression for potential. But potential is looked at as work done over charge. So the expression for work we shall get will eventually, upon integrating this from infinity, say, to r, will eventually give us an expression for potential as charge as the constant times charge out of r for now. So potential will be equal to the constant we have been using, 1 out of 4 pi epsilon times the charge out of r. If you compare it with intensity, the only difference is here, that the one for intensity r is squared, the one for potential r is just r. I will expose this fully in our next interaction, but allow us to attempt to interpret this number here. And I will start with electric potential, which is part 3, since we already know how to calculate field intensity. They want us to find potential at P. That means the first thing we need to do is to identify the length Q1P. By Pythagoras theorem, you will get this length, 400 plus 225, and that will give you 25 centimeters. You are supposed to show that quick working there. After showing that quick working and knowing that our potential, I said I'm going to start from potential since it is what we intend to, we don't know yet. If I start with 3, using potential, which is noted with V as K times charge over R, our potential at P is also going to be due to this charge and that charge. And given that it is K, it is therefore going to be 9. Potential at P due to Q1, let me call it that, will be 9 times 10 to the power 9 times the charge at Q1, which is 3 times 10 to the negative 6, all divided by the distance now, which is 25 times 10 to the negative 1. Remember, this is not squared. So we get that potential at Q at P due to that. The potential at P again, but now due to charge Q2, we repeat the same pattern. It is still the constant, 9 times 10 to the power 9, times the charge, which is this time negative 2 times 10 to the negative 6, over the distance. The distance now is 15, which is 15 times 10 to the negative 2. Now, the total potential at P will now be given by the sum of these two values. And since potential is scalar, when we add these two values, we add them directly. We will add the two values directly there. And what do we get? If you computed very well, the first one should have given us 10,800. These are volts. And the second one, this is 8,000, I think. And the second one, this one gives us a value of negative 1, 2, and 4 zeros, negative. So the total potential is obtained by doing the mathematics. The potential is obtained by doing the mathematics, and we'll get that potential at P by adding. The potential at P will give you a value of 12,000 negative. When we add, we get that as the total potential. Our time is fast spent, but we can now move to the last part. There is this part which is saying, find the location. Find the location of a point between Q1 and Q2 where the electric potential is 0. I am excluding this because I believe with the first example we can do. The location, for the location we use a simple approach. We let between Q1 and Q2, which is 20 centimeters, somewhere, let the point say be n. We let the distance from one charge be x. It means the distance from the other charge will be 20 minus x, because the total distance is 20. So using our expression for potential as k times charge out of r, we shall get that the potential there, the location at which the potential will be 0, the potential will be 0 when our VQ1n is equal to VQ2n. So if we get the potential due to this charge at that point using that distance, it should be equal to the potential due to that charge at this same point using 20 minus x. And therefore, our charge, which is 3, our 9 times 10 to the power 9 times 3 times 10 to the negative 6 out of x at this point should be equal to our 9 times 10 to the power 9 times the charge there, which is negative 2, times 10 to the negative 6 out of 20 minus x. Using that approach, we are able to determine the value of x, and therefore we can judge whether the potential will be closer or near. And since we have this similar and this similar, it means we are saying 3 out of x is equal to negative 2 out of 20 minus x. So we simply solve that expression. We simply solve that expression. And what happens when we are solving that? What happens? If we are using this condition, we put a negative here. The reason we put a negative here is that when we are adding, I think I can rub off this part. The reason we put a negative there is that VP Q1 plus that PQ2 n should be equal to 0. And it is 0 when they are additive inverses. So when we compute, we are able to get our 2x now positive. Our 2x becomes equal to our 3 into 20 minus x, and therefore our 5x becomes 60, and our x will be 12 centimeters. So it means if you press a charge 12 centimeters away from Q1, then you would be able to get a potential of 0. Or if you pressed it 8 centimeters away from Q2, you would be able to get the potential as 0. Our time is fast spent, as I told you. Questions will be left for you. You have the electric field intensity at P to calculate. And when we meet next, now that there will only be one derivation to show you how we get this, we should be able to, in our next meeting, do several examples of the same nature. And I am sure you will be able to proceed confidently with numbers of this nature. I want to thank you. I want to thank the management of BBS TV and wish you a very good weekend. There is work that I hope you've been able to capture some, but you can get in touch with me on my email for more work on practice. Please use the question bank book, UACE for physics, to get more work here that you can practice between now and then. Enjoy the weekend. Have a nice day. God bless you.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi lusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweeweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamune.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.
Wamune.
Congo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzannyisa by'abaana byonna mu nsi tubirina. Ate ng'abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Nnaggalabi nga bwakayisa Buddo Junior.
Official takes the crown, Papa Bosse with the best in town. Official new chapter, anti new chapter.